The Amazon has been running for millions of years, through ice ages and mass extinctions, through the rise and fall of the animals that surrounded it, through every change the planet has thrown at this part of the world. The river kept moving, warm, dark, and endlessly patient. And in all that time, it has been doing something to the animals inside it. Not the warm blooded ones, not the mammals and the birds that burn energy just to stay alive, that spend most of what they eat simply keeping their bodies at temperature. The Amazon has been doing something to the other kind, the ones that let the river do that work for them, the ones that take the warmth the water offers and spend what they save on something else entirely. They grow, and they keep growing, year after year, decade after decade, in a river that never gets cold enough to slow them down, in a system so rich with life that something is always within reach. The Amazon does not produce monsters by accident. It produces them the way a river produces everything, slowly, steadily, without ever once being in a hurry. What those millions of years have produced, the things moving through this water right now, unhurried and ancient and far larger than most people know. Tonight, we go into the Amazon, into the dark water, into the stories of the cold blooded things that own it. But before we do, if you enjoy videos like this, calm, gentle, and filled with science wonders, please hit the like button and subscribe. And let me know in the comments, is it late where you are right now, or are you starting your day with this? Now, let's begin. Every landscape carries its own set of biological rules, shaping which bodies flourish and which remain modest. Across much of the world, one of the clearest patterns appears among mammals and birds. Animals living in colder climates often grow larger than their close relatives living in warm regions. Larger bodies lose heat more gradually, holding precious warmth through long winters. Smaller bodies release heat more easily, which becomes an advantage where sunshine rarely fades. This pattern became known as Bergmann's rule, and for warm blooded creatures, it has guided body size across continents for generations of scientific study. The distinction begins with the way different animals manage temperature. A warm blooded animal keeps its body heated from within, burning food every hour to maintain a stable internal condition, whether the morning is cold or the afternoon is hot. A cold blooded animal follows another path. Its warmth comes from the surrounding world. Sunlit rocks, warm water, and heated soil provide the energy needed for muscles, digestion, and movement. Food still fuels life, though far less of it disappears into the continual expense of producing body heat. Near the middle of Earth, the Amazon remains warm through every season. Average water and air temperatures stay close to 27 degrees Celsius, or 81 degrees Fahrenheit, with comparatively little change across the year. Under Bergmann's rule, this environment favors smaller warm blooded animals because shedding excess heat becomes easier with a reduced body size. Many Amazon mammals reflect that pattern. They are often smaller than relatives living in cooler forests and grasslands far from the equator. Fish, reptiles, and amphibians follow another biological script entirely. Constant warmth does not burden them with overheating in the same way. Instead, environmental heat becomes a resource that accelerates digestion, movement, and growth whenever food is available. Every meal can contribute more directly toward building muscle, bone, scales, or stored energy because relatively little is diverted into maintaining an internal furnace that never switches off. Another difference stretches across an entire lifetime. Most mammals reach adulthood, complete their physical development, and remain close to the same overall size for the rest of their lives. Many reptiles, fish, and amphibians continue growing year after year. Growth may become slower with age, though it rarely stops altogether. Survival becomes the greatest limit. As long as food remains plentiful and serious injury or predation does not end life, the body continues adding mass with remarkable patience. The Amazon offers an unusual combination of conditions that supports this strategy. Warm temperatures encourage active metabolism every month of the year. Rivers, flooded forests, and connected waterways provide an immense supply of prey. Once an individual reaches the top of the food web, very few natural enemies remain capable of stopping that steady accumulation of size. Time itself becomes one of the greatest advantages available. Viewed through this lens, the Amazon is less a factory producing giants than a place where biological limits are unusually distant. The environment supplies warmth without charge. Prey arrives in extraordinary abundance, and the oldest cold blooded hunters continue adding weight through the passing years. Their immense bodies emerge from persistence, supported by a landscape that has sustained the same remarkable equation across millions of years. Weight more than length tells the true story of the green anaconda. Another snake may stretch farther across the ground, yet none carries the same immense mass. The green anaconda, known scientifically as Eunectes murnus, can reach about 550 pounds and extend beyond 29 feet, which is about 8.8 meters. At its thickest point, its body exceeds 12 inches in diameter, which is about 30 centimeters. Those dimensions place it among the largest reptiles alive, built less like a ribbon and more like living muscle, shaped for water. Its closest rival is the reticulated python of Southeast Asia. That species sometimes surpasses the anaconda in total length, though its body remains much narrower. An anaconda of similar length may weigh nearly twice as much because almost every part of its body has expanded into powerful coils. This extraordinary girth transforms it into a predator capable of overpowering prey that would challenge many other large snakes. Within the species itself, another striking pattern appears. Females become dramatically larger than males, creating one of the strongest examples of size difference between the sexes found among reptiles. A mature female may outweigh several adult males combined. This larger frame allows her to carry developing young, since green anacondas give birth to live offspring instead of laying eggs. Greater body mass also increases the range of prey she can capture, creating advantages that continue throughout her long life. Life in slow moving water has shaped nearly every feature of the anaconda's head. Its eyes and nostrils rest high on the skull, allowing almost the entire body to remain underwater, while those small openings stay above the surface. From a distance, they resemble little more than floating leaves or scattered debris. The rest of the animal blends into muddy channels, flooded grass, and tangled vegetation until movement brings another creature within reach. Finding prey depends on several senses working together. The tongue gathers tiny scent particles from the air and water, carrying them into specialized organs inside the mouth that interpret chemical traces. Heat sensitive pits along the upper lip detect the warmth given off by nearby animals. Vibrations also travel through the lower jaw whenever another body disturbs the ground or surrounding water. Each source of information joins the others, creating an exceptionally detailed picture of nearby life without requiring constant movement. Capturing prey marks only the beginning of the process. Flexible ligaments connect the lower jaws, allowing the mouth to expand far beyond the width suggested by the skull alone. Bones spread apart without separating, making room for animals several times wider than the snake's head. A capybara, a deer, or even a caiman can disappear gradually into the throat, swallowed whole through patient waves of muscular movement. Once feeding ends, the pace of life changes again. Digestion awakens with tremendous efficiency, while nearly every other activity declines. After consuming one substantial meal, an anaconda may live for many weeks, sometimes even months, without eating again. During this period, its energy demands remain astonishingly low compared with those of a warm blooded hunter carrying the same weight. Every successful meal stretches across an extraordinary span of time, allowing growth to continue while expending only a modest share of the calories stored within its immense body. Scientific discovery sometimes arrives with the realization that something familiar has been carrying another identity all along. For generations, every green anaconda encountered across northern South America was placed into a single species. Their immense bodies appeared alike, their habits seemed nearly identical, and the rivers connecting their ranges encouraged the assumption that they all belonged to one uninterrupted lineage. Careful genetic study eventually revealed another story, one written beyond outward appearance. In February of 2024, an international research team brought together 15 scientists representing 9 countries to examine that long standing assumption. Among them was Dutch biologist Freek Vonk, whose expedition into remote Amazon waterways gathered genetic material from living snakes across different regions. The laboratory results confirmed a pattern that had gradually emerged over years of investigation. Two distinct species had been sharing the name green anaconda, separated by an evolutionary history much deeper than anyone had recognized. The newly identified species received the scientific name Eunectes acaima, commonly called the northern green anaconda. Its southern relative retained the familiar scientific name Eunectes murinus. Their difference reaches approximately 5.5% across sections of their deoxyribonucleic acid. Within evolutionary biology, that degree of separation represents an extraordinary distance. At comparable genetic regions, the gap resembles the difference measured between modern humans and chimpanzees, illustrating that these immense snakes have followed independent paths for an immense span of time. Tracing those paths backward leads into an Amazon unlike the one flowing today. Around 10 million years ago, the rising Andes Mountains continued reshaping northern South America, redirecting rivers, creating wetlands, and separating animal populations that had once shared connected habitats. As waterways shifted across the landscape, groups of ancestral anacondas gradually became isolated from one another. Generation after generation, each population accumulated its own genetic changes until two distinct species emerged from the same ancestral stock. The field expedition provided another memorable moment beyond the laboratory findings. Researchers encountered an enormous female northern green anaconda estimated to exceed 26 feet, which is about 7.9 meters, and weighing roughly 440 pounds. She rested almost entirely underwater, revealing little of her tremendous size except the outline visible through the river. Her presence illustrated how an animal of astonishing scale could remain scientifically misunderstood despite centuries of exploration within the Amazon basin. That realization carries unusual weight. One of the largest reptiles on Earth existed as a separate species while remaining formally undescribed by science until 2024. Nothing about the snake had recently evolved into existence. Human understanding had simply taken longer to catch up with biological reality. The Amazon still contains places where immense animals continue living beyond the reach of complete scientific knowledge. Further evidence soon deepened that perspective. A study published during December of 2025 in the Journal of Vertebrate Paleontology examined fossil evidence and evolutionary history, concluding that anacondas had already achieved their extraordinary size at least 12 million years ago. Their immense bodies represent no recent experiment shaped by modern conditions. They reflect a solution refined across immense stretches of geological time, remaining effective through changing rivers, shifting continents, and countless generations that carried the same enduring design into the present. Predators often rely on speed, endurance, or venom, yet the green anaconda has committed itself to another strategy, one built around timing. Every part of its body is designed for the brief moment when waiting comes to an end. Hours may pass without noticeable movement, though the animal loses little by remaining still. Warm water supports its immense weight, and an exceptionally low metabolism allows it to spend very little energy while the surrounding world continues its ordinary rhythms. Its patterned skin blends with floating vegetation, tangled roots, and dark water stained by leaves carried downstream. Fish pass nearby, birds drink at the edge, and mammals descend toward the river without recognizing the shape resting almost entirely below the surface. The anaconda invests in concealment instead of pursuit. Distance matters very little, because every successful hunt begins only after prey has already entered striking range. The first movement arrives with astonishing speed. Rows of backward curving teeth seize the victim in an instant. Those teeth exist for gripping rather than cutting, functioning like hooks that sink deeper whenever prey struggles to pull away. Escape becomes increasingly difficult because every effort to retreat tightens the hold. The snake never attempts to tear flesh apart. Holding firmly is all that is required before the rest of its body joins the encounter. Powerful coils wrap around the captured animal, one loop after another. Popular stories often describe snakes crushing bones, though careful study paints another picture. Constriction works by preventing the chest from expanding enough to draw another breath. Blood circulation also becomes disrupted as pressure rises around the body. Oxygen can no longer reach vital organs efficiently, and unconsciousness arrives rapidly. Death follows through suffocation and circulatory failure rather than shattered skeletons. Measurements taken from large, constricting snakes suggest that an anaconda may generate pressures exceeding 90 pounds per square inch. That force resembles the pressure experienced beneath a column of water approximately 200 feet deep, which is about 61 meters. Such strength develops through the coordinated action of hundreds of muscles extending almost the entire length of the body. Every coil contributes another layer of controlled force until movement gradually disappears. The menu available to such a predator reflects that remarkable capability. Capybaras, the largest rodents on Earth, regularly fall within its hunting range. Deer, wild pigs, turtles, and black caimans also appear among documented prey. Rare verified reports even describe attacks on jaguars, demonstrating that almost any animal approaching the river may become vulnerable if size and circumstance align in the snake's favor. Swallowing begins only after the struggle has ended. The flexible skull and expandable ligaments described earlier allow prey to enter the mouth intact. Muscles along the throat advance the meal through alternating waves of contraction, drawing the entire body inward without chewing. Once feeding is complete, another extraordinary transformation begins inside the digestive system. Organs that had been operating at minimal activity awaken with astonishing intensity. The stomach releases powerful acid along with digestive enzymes capable of breaking down skin, muscle, and even much of the skeleton. Processing an entire caiman may require several days, though the feast sustains the snake for weeks or months afterward. Few reptiles display such dramatic shifts between prolonged fasting and overwhelming digestive activity, and no warm-blooded predator can suspend and restart its metabolism with the same extraordinary efficiency. Across broad rivers and flooded forests, another giant carries authority through presence alone. The black caiman, known scientifically as Melanosuchus niger, stands as the largest predator in the Amazon basin and the largest living member of the alligator family. For countless generations, it has occupied the highest level of the freshwater food web, shaped by a body that wastes little energy and a design refined through immense spans of evolutionary time. Adult males commonly reach between 13 feet, which is about 4 meters, and 16 feet, which is about 4.9 meters, while weighing around 770 pounds. Exceptional individuals approach 20 feet, which is about 6.1 meters, and exceed 1,000 pounds. Such dimensions place the black caiman among the heaviest reptiles on Earth. Every movement reflects tremendous strength, though much of its life unfolds with careful economy rather than constant activity. Its name comes from scales so deeply pigmented with melanin that they appear almost black. This coloration serves more than appearance. During daylight hours, darker skin absorbs solar warmth with remarkable efficiency. Heat collected while resting along riverbanks becomes stored energy, later supporting digestion, muscle activity, and prolonged hunting. The animal carries no internal furnace. Sunlight provides the thermal reserve that powers nearly every biological process once darkness returns. The shape of the skull reflects the same careful adaptation. Eyes and nostrils sit high upon the head, allowing nearly the entire body to remain underwater while maintaining awareness of the world above. From that position, the caiman surveys riverbanks, floating vegetation, and passing animals with only a small portion of its body exposed. Little disturbance marks its presence, allowing opportunities to develop without unnecessary movement. Night brings the period of greatest activity. Specialized cells behind the retina reflect available light, greatly improving vision after sunset. Faint ripples, distant splashes, and shifting outlines become enough to guide an accurate strike. Sensitive pressure receptors scattered across the jaws detect tiny disturbances moving through the water, allowing prey to be located even when visibility becomes poor. Sight, vibration, and patient observation combine into a hunting strategy that depends on precision rather than speed. Very few Amazon predators possess such a broad appetite. Fish form an important part of the diet, though turtles, capybaras, deer, tapirs, birds, and snakes may also be taken whenever opportunity appears. Large black caimans have even been documented feeding upon anacondas. Rare observations describe successful attacks on jaguars approaching the water's edge, illustrating that almost every animal sharing this ecosystem occupies the caiman's potential menu under the right conditions. Reaching adulthood changes the balance of survival dramatically. Hatchlings and juveniles face danger from birds, larger fish, and mammals. Yet a fully grown black caiman stands beyond the reach of nearly every predator living alongside it. One unusual exception has been observed among families of giant river otters. Working together with remarkable coordination, several adults have occasionally succeeded in killing a young caiman before it reached its full size. Encounters involving mature individuals remain extraordinarily uncommon. The black caiman, therefore, represents another expression of the biological pattern flowing through these waters. Warmth gathered from the surrounding world fuels an immense body, while abundant prey supports continued survival across decades. At the summit of the Amazon's rivers, that combination has produced a reptile whose dominance rests upon patience, efficient energy use, and an environment that continues providing exactly what its ancient design requires. There was a period when the greatest danger facing the black caiman came from neither drought nor rival predator. It came from distant cities, far beyond the Amazon basin, where polished leather carried status and fashion often outweighed concern for the living world. The thick hide that had protected this reptile for millions of years became a valuable commodity, drawing hunters deep into river systems that had remained largely unchanged for ages. Throughout the middle decades of the 20th century, commercial hunting intensified across much of northern South America. Black caimans were harvested primarily for their skins, which supplied luxury markets in Europe and the United States. Shoes, handbags, belts, and other leather goods created steady international demand. Countless rivers that had long supported healthy populations gradually lost their largest breeding adults, the very animals most important for maintaining future generations. By the 1970s, the consequences had become impossible to ignore. Scientists estimated that roughly 99% of the black caiman population had disappeared across much of its historical range. Few large predators have experienced such an extreme decline within such a short period. Areas once occupied by dominant adult caimans became strangely empty, leaving stretches of river where one of the Amazon's defining reptiles had nearly vanished. Governments eventually responded with coordinated protection. Peru, Brazil, and Colombia prohibited commercial hunting during 1973. 2 years later, in 1975, the species received protection through Appendix 1 of the Convention on International Trade in Endangered Species of Wild Fauna and Flora. International trade in black caiman skins collapsed, removing the economic force that had driven decades of relentless exploitation. Recovery began with surprising speed. Part of that resilience came from a biological strategy already woven into the species long before humans entered the story. Female black caimans produce large clutches, laying as many as 65 eggs during a single nesting season. Even though many hatchlings never survive to adulthood, such reproductive output provides opportunities for populations to rebuild much faster than similarly sized mammals, whose young are usually born only one or two at a time. Their efficient metabolism also played an important role. Cold-blooded reptiles require only a fraction of the food needed by warm-blooded predators of comparable size. Surviving adults could regain body condition without exhausting local prey populations, even after years of ecological disruption. Every successful hunt carried enough energy to sustain long intervals, allowing adults to invest more resources into reproduction and survival, while food webs gradually recovered. Protection of nesting habitat further strengthened this return. Female caimans defend their nests with remarkable dedication, remaining close as eggs develop beneath carefully gathered vegetation. Once the young hatch, mothers often guide them toward sheltered nursery areas, guarding them through the earliest and most vulnerable stage of life. Such parental care increases survival enough to support steady population growth whenever hunting pressure remains low. Today, researchers estimate that between 25,000 and 50,000 black caimans inhabit the Amazon basin. Those numbers remain far below historical abundance, yet they are sufficient for the species to reclaim much of its ecological role as an apex predator. Rivers that once seemed emptied of these reptiles again support breeding adults whose presence influences every level of the surrounding food web. Their return reflects effective conservation, strengthened by a life history shaped across millions of years to endure hardship and begin again whenever conditions allow. Some creatures seem to belong to a particular era, while others appear almost untouched by the passing of geological time. The arapaima belongs to the latter. Swimming through broad rivers and seasonally flooded forests, it carries a body plan that has endured through immense environmental change, remaining recognizable across millions of years, while landscapes around it transformed beyond recognition. The arapaima, known scientifically as Arapaima gigas, is the largest freshwater fish in South America. Exceptional individuals can approach 10 feet in length, which is about 3 meters, and weigh as much as 440 pounds. Even among the largest freshwater fishes on Earth, it occupies an extraordinary place. Fossils discovered in what is now Colombia reveal animals almost indistinguishable from the modern arapaima, dating back more than 13 million years. Long before the Amazon basin assumed its present form, this giant was already patrolling rivers that flowed through a very different world. Across its range, people know it by different names. In Brazil, it is commonly called pirarucu, a word from the Tupi language referring to the reddish coloring that appears on the scales near its tail. In Peru, it is more often called paiche. Although the names change from one region to another, each refers to the same remarkable survivor whose lineage has persisted through ages of shifting climates, rising mountains, and changing waterways. Its feeding equipment reflects that long evolutionary history. The roof of the mouth contains a hard, bony surface lined with countless small, gripping teeth. When prey drifts within reach, the jaws swing open with astonishing speed. Water rushes inward as though drawn by an invisible force, creating a powerful vacuum that pulls fish or other nearby animals directly into its mouth. The strike often produces a sharp clapping sound across the water, lasting only a moment before the surface becomes smooth once again. Its menu is unusually broad. Fish form much of its diet, although birds, insects, fruit, and small mammals may also be taken whenever opportunity presents itself. Rather than specializing in one particular prey, the arapaima makes use of whatever seasonal abundance the flooded forest provides. Such flexibility has helped sustain the species through countless environmental fluctuations. Its most remarkable adaptation, however, is neither its size nor its hunting method. The arapaima breathes air. Every 5 to 15 minutes, depending on activity and water conditions, it must rise to the surface and gulp fresh air. That breath passes into a highly modified swim bladder whose richly supplied blood vessels allow it to function much like a lung. The fish therefore depends upon regular visits to the surface throughout its entire life. This ability grants access to waters that many other large fish cannot tolerate. During seasonal floods, enormous quantities of fallen leaves and other vegetation decay beneath the water. That process consumes dissolved oxygen until conditions become unsuitable for most large aquatic animals. The arapaima continues to thrive because it no longer depends primarily upon oxygen dissolved within the water itself. It has entered an ecological space with remarkably little competition, occupying a role that has remained successful for more than 13 million years without requiring fundamental change. Few natural materials have attracted as much attention from engineers as the skin of the arapaima. At first glance, its scales appear thick and ordinary, arranged in overlapping rows that shimmer with muted color beneath the water. Closer examination reveals something altogether different. Every scale is built as a layered defensive structure whose design has challenged some of the finest materials scientists in the world. Each scale begins with a hard, mineralized outer surface marked by shallow ridges and corrugations. This exterior forms the first barrier against teeth, claws, and other sharp impacts. Beneath that rigid shell lies an entirely different material, composed of many layers of collagen fibers. Those fibers are not stacked in parallel sheets. Instead, every successive layer rotates slightly from the one above and below it, producing a complex arrangement known as a Boolean structure. The pattern resembles sheets of plywood only in the broadest sense. At a microscopic level, each collagen layer points in a different direction, creating a twisting internal architecture that changes continuously throughout the thickness of the scale. Any force entering from the outside must travel through fibers oriented along constantly shifting angles. The path forward becomes increasingly difficult as the impact spreads sideways through the surrounding material instead of driving straight inward. This design proves especially valuable against one of the Amazon's most efficient predators. Piranhas possess razor-sharp teeth capable of slicing flesh with extraordinary precision, and their bites can even score or cut bone under favorable conditions. When one of those teeth strikes the arapaima's scales, it may scratch or indent the hardened exterior, yet the underlying collagen layers redirect the remaining force through multiple directions. Energy that might otherwise split the scale becomes dispersed across a much larger area. Laboratory experiments have demonstrated the effectiveness of this arrangement under carefully controlled conditions. Researchers subjected arapaima scales to mechanical testing using penetrating instruments designed to imitate the concentrated force produced by piranha teeth. The results showed that the scales resisted fracture even after substantial impacts. Instead of shattering, they flexed, absorbed energy, and preserved the protective barrier surrounding the fish. Toughness and flexibility worked together, producing a defense that neither property could achieve independently. Such findings drew the attention of researchers studying advanced protective materials. Scientists at the University of California, Berkeley, together with investigators at the Massachusetts Institute of Technology, examined the layered organization of these scales in remarkable detail. Their goal extended far beyond understanding one Amazon fish. They hope to adapt the same structural principles for lightweight protective equipment, flexible body armor, and impact-resistant materials capable of resisting damage while remaining practical for everyday use. Nature had already solved many of the engineering challenges confronting modern designers. Instead of relying upon greater thickness or heavier construction, the arapaima achieved protection through internal organization. Every microscopic layer contributes to the whole, allowing strength to emerge from arrangement as much as from composition. The fish carries this solution effortlessly through waters where sharp teeth remain an ordinary part of daily life. Across more than 13 million years, countless generations refined that remarkable design without laboratories, computers, or manufactured alloys. Evolution tested each small variation against real predators, preserving structures that performed most effectively. The armor covering today's arapaima, therefore, represents millions of years of uninterrupted experimentation, offering lessons that human engineering has only recently begun to understand and carefully translate into materials of its own. Water can become a conductor of astonishing possibilities. Among the roots, flood channels, and slow-moving tributaries of the Amazon lives a fish that transformed electricity into a hunting tool long before humans understood the phenomenon itself. Despite its familiar name, the electric eel is not truly an eel. It belongs to the knifefish lineage and shares a closer evolutionary relationship with catfish than with the elongated marine eels it resembles. For more than 2 centuries, scientists believed every electric eel belonged to a single species. Careful genetic study eventually revealed a more complex picture. During 2019, Researchers formally divided the group into three distinct species. They became known as Electrophorus electricus, Electrophorus varii, and Electrophorus volti. Each occupies different regions of northern South America, reflecting long periods of separate evolutionary history across river systems that gradually diverged over immense spans of time. Among those newly recognized species, Electrophorus volti immediately attracted extraordinary attention. Found primarily within rivers draining the Brazilian Shield, it produces the strongest electrical discharge ever measured in any living organism. The maximum recorded output reaches approximately 860 volts. For comparison, a standard household electrical outlet in North America supplies about 120 volts, while a medical defibrillator commonly delivers around 200 volts during treatment. The discharge of this remarkable fish exceeds 4 times the electrical potential of that medical device. Such power does not emerge from a single organ acting alone. Nearly 6,000 specialized cells, known as electrocytes, fill much of the animal's elongated body. Arranged in long columns, extending across roughly 80% of its length, these cells behave much like countless tiny biological batteries connected one after another. Each cell contributes only a small electrical difference, yet together they produce an astonishing cumulative discharge capable of affecting animals many times larger than the fish itself. The consequences can be dramatic. A single powerful pulse may stun a horse entering shallow water, disrupting muscles and overwhelming the nervous system for valuable moments. Human fatalities have also been documented, although the electricity itself rarely serves as the direct cause of death. Instead, victims rendered unconscious may lose the ability to remain above the surface, leading to drowning before assistance can arrive. Powerful attacks represent only one part of the eel's electrical language. Much weaker signals flow continuously through the surrounding water as it explores its environment. These discharges measure fewer than 10 volts and allow the fish to sense nearby objects by detecting tiny distortions within the electric field surrounding its body. Living animals, submerged branches, and uneven river bottoms all alter that invisible field in distinct ways. The eel therefore navigates and locates prey through electricity, building a detailed picture of places where vision alone offers little guidance. When prey approaches within striking distance, the electrical strategy changes instantly. Low-level pulses give way to an intense burst that overwhelms muscles and nervous tissue almost simultaneously. Fish lose coordinated movement, making escape nearly impossible. The predator closes the remaining distance with little resistance before swallowing its meal whole. Like several other giants already encountered in these waters, electric eels continue growing throughout life. New vertebrae are added as the body lengthens, allowing exceptional individuals to exceed 8 feet, which is about 2.4 meters. Every additional year brings greater size, more electrocytes, and increased electrical capacity, extending a biological design that has remained among the most extraordinary inventions ever produced by the living world. Ideas sometimes travel in unexpected directions. A creature moving through Amazon rivers became part of a chain of thought that eventually transformed the modern world. Long before wires stretched between cities or machines depended upon stored electricity, natural philosophers looked toward living animals for clues about forces that could neither be seen nor held. Among the most influential examples stood the electric eel, whose remarkable anatomy offered a working demonstration of electrical power produced entirely by living tissue. During the closing years of the 18th century, Italian physicist Alessandro Volta closely followed reports describing animals capable of generating electricity. He exchanged ideas with researchers who had examined electric fish, including electric eels, whose internal organs revealed thousands of repeating structures arranged in orderly columns. Those observations encouraged a different way of imagining electrical generation. Instead of relying upon a single powerful source, countless small units could contribute modest amounts of electrical potential that accumulated into something far greater when connected together. The body of the electric eel already followed exactly that principle. Approximately 6,000 specialized electrocytes are stacked one after another through much of the animal's length. Every individual cell produces only a tiny electrical difference. Joined in long columns, each contribution adds to the next until the combined discharge becomes powerful enough to stun large animals. The arrangement functions according to the same fundamental concept later embodied within the earliest practical battery. Volta translated that biological pattern into technology. Thin disks of zinc and copper became the repeating elements. Between each metal layer rested cloth soaked in salt solution, allowing electrical charge to move from one level to the next. The resulting structure became known as the voltaic pile, the first true electric battery. Its familiar stack of alternating materials echoed the layered organization already perfected within the electric eel, replacing living cells with carefully arranged metals while preserving the same underlying strategy of accumulation. From that breakthrough, an unbroken thread extends across more than 2 centuries of invention. Every portable radio, flashlight, television, remote, laptop computer, mobile telephone, and electric vehicle depends upon batteries built upon the same central principle. Materials have changed dramatically. Performance has increased beyond anything Volta could have imagined. Even so, each design still depends upon many repeating units working together, each adding its own small contribution until the combined electrical potential becomes useful. The language of electricity also preserves this history. The standard unit used to measure electrical potential bears the name volt, honoring Alessandro Volta and his pioneering work. Every mention of voltage, therefore, carries a reminder of that early period when scientists studied remarkable creatures alongside minerals and metals, searching for patterns shared across nature. Seen across millions of years, the sequence feels almost effortless. Evolution shaped electrocytes through countless generations until they formed one of the most effective biological electrical systems on Earth. Human curiosity eventually recognized the same arrangement and translated it into engineering. A predator drifting through Amazon waters had already demonstrated the solution long before laboratories, factories, or electrical networks existed. The river carried that design across deep time, waiting until another species learned how to read the lesson written within a living body. Far below the river's sunlit surface, another giant follows a very different path through the Amazon. It does not patrol flooded forests like the arapaima, nor does it wait among reeds like the anaconda. Its world lies along the deep channels where suspended sediment turns the water into a moving veil. Within that dim current swims the piraíba, the largest catfish in the Amazon, a predator whose life remains only partly understood despite its immense size. A fully grown piraíba, formerly known as Brachyplatystoma filamentosum, can reach 9 feet in length, which is about 2.7 meters, and weigh more than 400 pounds. Its broad head tapers into a muscular body built for steady endurance instead of sudden bursts of speed. Long whisker-like barbels extend from its mouth, tasting the surrounding water for chemical traces released by injured fish or drifting animals. Vision plays only a minor role where sunlight rarely penetrates, so scent and vibration become the primary guides through the river. Its mouth is immense, forming a cavern capable of engulfing prey that would seem impossibly large for most freshwater fish. Fine teeth curve backward from the jaws, serving as hooks rather than cutting tools. Once an animal is drawn inside, every attempt to pull away presses it farther toward the throat. Escape becomes increasingly difficult with each movement, allowing the fish to swallow prey whole before the current carries another opportunity away. Stories about enormous catfish consuming people have circulated throughout Amazonian communities for generations. Many belong to local tradition, growing larger with each telling. A small number, however, rest upon documented forensic evidence collected in Brazil. Human remains have been recovered from the stomachs of piraíba, confirming that this species has consumed adult humans. These findings do not suggest that the fish actively hunts people. Most specialists consider such cases to involve drowning victims carried downstream, where an opportunistic predator fed upon remains already in the water. Even so, verified records place the piraíba among the very few freshwater fish known to have consumed adult humans. Its journey through the river system is almost as remarkable as its appetite. Adult piraíba migrate thousands of miles across the Amazon basin during their lives, traveling between feeding grounds within flooded forests and distant breeding areas in major river channels. These migrations rank among the longest known for freshwater fish, linking ecosystems separated by enormous distances while transporting nutrients and energy across the basin. Life in deep water demands specialized adaptations. Oxygen levels often decline where decaying organic matter accumulates, leaving conditions unsuitable for many species. The piraíba tolerates these environments with impressive efficiency, allowing it to exploit regions where competition becomes far less intense. Combined with tremendous size and powerful jaws, this advantage places large prey within reach that smaller predators could never overcome. People have long valued the flesh of the piraíba, making it an important commercial catch across many Amazonian communities. Fishermen know where these giants often travel, although locating them remains challenging because of their preference for deep channels and extensive migrations. Scientists face the same difficulty. Reliable population estimates remain elusive, leaving one of the Amazon's largest predators moving through the river, with much of its story still unwritten. Across the leaf litter, where fallen branches soften into rich soil, and every layer shelters another form of life, one hunter moves without haste. Its footsteps are almost impossible to hear, yet each one carries the weight of the largest spider on Earth. The Goliath birdeater has inspired stories far larger than itself, although its daily life is shaped far more by patience than by spectacle. Known scientifically as Theraphosa blondi, this tarantula can weigh as much as 6.2 ounces and stretch its legs across 12 inches, which is about 30 centimeters, giving it a span comparable to a dinner plate. Even at that size, much of its body remains low against the forest floor, where shades of brown blend naturally with damp leaves, bark, and scattered roots. Camouflage serves it better than speed, allowing the spider to disappear until movement nearby reveals an opportunity. Its common name suggests a hunter of birds, yet birds form only a small and infrequent part of its diet. Most meals consist of large insects, frogs, lizards, small snakes, and other animals that wander within striking distance. Powerful legs pin struggling prey, while curved fangs deliver venom that begins breaking down tissues. For healthy humans, that venom is considered medically mild, producing strong, localized pain and swelling instead of life-threatening effects. Physical strength remains the spider's greatest advantage, allowing it to overpower creatures that would challenge far smaller relatives. Like every tarantula, the Goliath birdeater depends upon external warmth to regulate its activity. The constant tropical climate of the Amazon keeps its body functioning through much of the year, supporting faster growth, more frequent hunting, and greater adult size than tarantulas living in cooler regions. Digestion, movement, and development all rise and fall with surrounding temperatures, linking the spider's life directly to the steady warmth of its environment. Defense relies upon more than formidable fangs. When threatened, the spider may rub specialized body parts together to produce a rasping hiss through a process called stridulation. The sound can be heard from 15 feet away, which is about 4.6 meters, creating an unmistakable warning before physical contact occurs. If the threat continues, the spider turns its abdomen toward the intruder and rapidly brushes loose thousands of microscopic barbed hairs. These airborne hairs lodge in skin and especially in sensitive eyes, causing intense irritation that can persist long after the encounter ends. Growth unfolds through repeated molts, each shedding the old outer skeleton to reveal a larger one beneath. Every successful molt brings additional size, provided food remains available and injuries are avoided. Females may survive for as long as 20 years, an extraordinary lifespan for an arthropod. Such longevity allows them to continue growing across many seasons, making the oldest females substantially larger than younger members of the same species. The Goliath bird-eater stands as another reminder that the Amazon shapes giants in many forms. Some dominate rivers, others rule the canopy, while this remarkable spider claims the forest floor through endurance, patience, and an anatomy refined across countless generations. Its presence reflects an ecosystem where even the smallest pathways may belong to creatures whose histories extend far beyond human memory. Stone ceilings rarely seem like hunting grounds, yet within certain caves of northern South America they become exactly that. High above the floor, where bats stream through narrow passages each evening and invertebrate waits with remarkable control. The Amazonian giant centipede has transformed an ordinary surface into an elevated trap, revealing a behavior that remained unknown to science until the early years of the 21st century. Scientifically known as Scolopendra gigantea, this formidable centipede reaches nearly 12 inches in length, which is about 30 centimeters, making it the largest living centipede species on Earth. Its elongated body is divided into many armored segments, each supporting a pair of powerful legs that work together with impressive coordination. The final pair differs from the others. Longer and stronger, these hind legs serve as anchors that grip uneven rock with exceptional force, allowing the animal to support its own weight while suspended upside down. Venom gives the centipede another decisive advantage. Its toxic mixture contains serotonin, histamine, and compounds capable of damaging tissue while interfering with normal muscle and cardiovascular function. A bite can produce severe pain, swelling, and localized necrosis in humans. Most healthy people recover with appropriate medical care, although severe complications have been documented and rare fatalities have been reported. For prey animals, however, the venom acts swiftly enough to prevent prolonged struggle, allowing the centipede to retain control despite attacking creatures close to its own size. The most extraordinary aspect of its biology emerged during observations inside a cave in Venezuela during the year 2005. Researchers watched giant centipedes clinging to the ceiling solely by their rear legs, while the rest of the body hung freely through open air. As bats flew past on their nightly departures, The waiting predator lunged downward, seized a victim with its front legs, and delivered a venomous bite before the animal could escape. The struggle unfolded while the centipede remained suspended above the cave floor, relying entirely upon its grip and muscular strength. This discovery surprised zoologists because nothing previously known about centipede behavior suggested such an aerial hunting strategy. The event was neither scavenging nor accidental contact. It represented deliberate ambush directed at healthy flying mammals. Success depended upon a rare combination of body mass, mechanical leverage, and venom potency. Smaller centipede species would struggle to maintain their hold, much less overpower an airborne bat while hanging inverted. The consistently warm Amazon climate encourages continual growth, producing individuals large enough to exploit this unusual opportunity. Although bats attract the greatest attention, they represent only one part of a highly adaptable diet. Frogs, lizards, insects, mice, and small snakes all become prey whenever circumstances permit. Strong jaws, flexible movement, and effective venom allow the giant centipede to exploit whatever suitable animal comes within reach. Such versatility places it among the dominant invertebrate predators of the Amazon understory, where countless smaller creatures share the same tangled landscape. The giant Amazonian centipede demonstrates that evolution can shape unexpected solutions without abandoning practical efficiency. Every segment, every hooked leg, and every droplet of venom contributes to a hunting strategy refined across immense spans of time. Within this forest, even a cave ceiling becomes another place where life discovers new ways to endure. A pattern begins to emerge once these remarkable creatures are viewed together instead of separately. The anaconda, black caiman, arapaima, electric eel, goliath birdeater, and giant Amazonian centipede seem to belong to entirely different worlds. One coils through rivers, another patrols the water's edge, another breathes air between dives, while others move across leaf litter or stone. Their bodies, behaviors, and hunting strategies differ profoundly. Even so, each relies upon the same biological principle, one that has steadily shaped their success across millions of years within the Amazon. Unlike mammals and birds, these animals do not produce large amounts of internal heat to maintain a constant body temperature. Their warmth comes primarily from the surrounding environment. In many parts of the world, that dependence would impose severe limits. Across the Amazon basin, however, steady tropical warmth transforms this apparent disadvantage into an extraordinary advantage. Energy that warm-blooded animals must dedicate to generating heat remains available for other biological purposes. Consider the jaguar, the largest warm-blooded predator of the Amazon. Even while resting, its body continuously consumes energy to maintain an internal temperature of approximately 38.5 degrees Celsius or 101 degrees Fahrenheit. Estimates suggest that an adult jaguar may require roughly 3,000 to 5,000 calories each day simply to sustain normal body functions, long before the costs of movement, hunting, reproduction, or recovery from injury are added. Heat itself becomes one of the animal's greatest daily expenses. A reptile of similar body mass follows a very different accounting system. An anaconda, for example, absorbs environmental warmth instead of producing most of it internally. Studies indicate that reptiles may spend as little as 1/10 of the maintenance energy required by mammals of equivalent size. Those saved calories do not disappear. They become available for building muscle, storing reserves, producing eggs, repairing damaged tissue, and extending survival through periods when food becomes scarce. Every successful meal, therefore, contributes more directly to future growth. This energetic efficiency helps explain why several Amazonian reptiles, fishes, and large arthropods continue growing throughout much of their lives. Biologists describe this pattern as indeterminate growth. Instead of reaching a sharply defined adult size before growth largely stops, these animals continue adding body mass whenever resources remain favorable. Each passing season offers another opportunity to become larger, stronger, and more capable of producing offspring. The forest's dependable warmth supports digestion, movement, and recovery through nearly every month of the year, allowing this gradual expansion to continue without the prolonged interruptions imposed by harsh winters elsewhere. The same strategy would falter in colder climates. Without sufficient environmental warmth, digestion slows dramatically, muscles lose efficiency, and hunting opportunities become increasingly limited. Growth stalls because too little usable energy remains available. Within the Amazon, those obstacles rarely dominate daily life. Rivers, flooded forests, and shaded ground provide dependable thermal conditions that allow these creatures to remain active through much of the year. The landscape supplies the warmth they require, leaving evolution free to invest their energy in size, reproduction, and remarkable longevity instead of manufacturing heat from within. Across this living tapestry, enormous bodies arise through different lineages, yet all are guided by the same enduring economy of energy, refined over immense spans of time and sustained by a forest that has long provided warmth without asking its inhabitants to create it themselves. Energy leaves its mark in ways that are not always visible at first glance. Every heartbeat, every breath, every muscle held ready for movement carries a cost. Across the Amazon, where warmth lingers through the changing seasons, that cost is paid very differently by mammals than by reptiles. Their lives unfold under the same sun, yet the balance sheets written inside their bodies follow separate rules that shape growth, survival, and the limits of size. The jaguar stands as the largest warm-blooded predator in this forest. Even while resting, it continuously burns fuel to maintain an internal temperature of approximately 38.5 degrees Celsius or 101 degrees Fahrenheit. Estimates suggest an adult jaguar may consume roughly 3,000 to 5,000 calories each day before accounting for the added demands of hunting, travel, injury, or raising young. An anaconda of comparable body mass follows another strategy. Because it relies upon surrounding warmth instead of producing its own, its basic energy requirements remain dramatically lower. After swallowing a large meal, it may not need to feed again for weeks or even months, drawing steadily upon stored reserves while expending comparatively little energy. Growth follows the same contrast. Once a jaguar reaches adulthood, its overall body size becomes largely fixed. Healthy adults may gain or lose weight with changing conditions, yet they do not continue increasing in length or overall structural size throughout life. An anaconda follows a pattern known as indeterminate growth. As long as food remains available and age does not limit survival, it can continue adding length and mass year after year. An individual at 10 years of age is commonly larger than it was at 3, and one that survives for 2 decades may become larger still, though the pace of growth gradually slows with age. Climate also shapes body size in more subtle ways. Ecologists have long observed that many warm-blooded animals tend to reach larger, average sizes in colder regions, a pattern widely known as Bergmann's rule. Tropical populations often remain smaller on average, although many exceptions exist. Among tigers, The Sumatran tiger is the smallest living subspecies, while the Siberian tiger reaches substantially greater size. Similar environmental influences can affect other mammals, though each lineage also responds to food availability, habitat, competition, and evolutionary history. Within the Amazon, these contrasting strategies create an unusual balance. Warm blooded mammals invest enormous amounts of energy into maintaining stable internal temperatures every hour of every day. Reptiles, large fishes, and many arthropods redirect much more of that available energy toward growth, reproduction, and long survival whenever environmental conditions remain favorable. The forest does not eliminate every limit on body size, yet its dependable warmth removes one of the greatest constraints facing animals that depend upon external heat. The outcome is a landscape where some of the largest and longest lived predators are scaled instead of fur covered, where decades may steadily add to an anaconda's mass, while a jaguar has long since reached its full frame. Both strategies have endured because each succeeds in different ways, although the Amazon offers an especially welcoming stage for creatures that allow the surrounding world to provide the warmth their bodies require. Every giant encountered along this journey owes part of its existence to a force that never hunts, never sleeps, and never stops moving. It is the Amazon River itself, a living engine stretching across much of South America, carrying warmth, nutrients, and life through an immense network of channels. Every predator described so far, from towering fish to immense reptiles and giant invertebrates, ultimately depends upon this flowing system. Without the river, the remarkable scale of these animals would never have emerged. The Amazon is the largest river system on Earth by the volume of water it releases into the sea. Approximately 20% of all fresh water entering the world's oceans arrives through this single drainage network. More than 1,100 tributaries feed its main channel, and 17 of those rivers each extend beyond 1,000 miles, which is about 1,609 kilometers. Together, they drain a basin covering roughly 2,700,000 square miles, an area comparable to the contiguous United States. Countless streams merge into larger rivers until the entire landscape functions as one connected circulation system. Water flowing through the main channel generally remains between 26 degrees Celsius or 79 degrees Fahrenheit and 30 degrees Celsius or 86 degrees Fahrenheit throughout the year. Those temperatures place many reptiles and large fishes within an ideal operating range. Digestion becomes faster, muscles recover efficiently, and animals depending upon external warmth remain active across every season. Instead of spending energy generating body heat, they can devote a much greater share of every meal toward growth, reproduction, tissue repair, and long survival. Seasonal rainfall transforms this system even further. During the wet season, water levels in some regions rise by approximately 30 to 45 feet, which is about 9 to nearly 14 meters. The expanding river spreads into surrounding forests, increasing its footprint by as much as 50%. Areas that recently supported walking animals become temporary waterways winding among standing trees. Branches, roots, and trunks form a completely different hunting landscape before dry conditions gradually return several months later. This annual flood creates one of the richest feeding grounds anywhere on Earth. Fish disperse into submerged forests to feed upon fruits, seeds, insects, and smaller fishes. Caimans patrol newly connected channels. Anacondas move between flooded trees in search of mammals, birds, and reptiles, entering unfamiliar water. Arapaimas exploit fresh hunting territory before returning to deeper channels as floodwaters retreat. Every seasonal expansion briefly rearranges the relationships between predator and prey, creating opportunities that exist only during this recurring stage of the river's cycle. The biological productivity generated by this network is almost beyond comprehension. Around 15% of all freshwater fish species known on Earth inhabit the Amazon basin, forming an enormous reservoir of prey that supports predators of exceptional size. The river continually delivers food, warmth, and habitat across an interconnected landscape unlike any other. It does far more than transport water toward the ocean. The Amazon operates as a planetary life support system, sustaining generations of giants through a combination of dependable warmth, immense biodiversity, and an endless current that has shaped this living world for millions of years. For several months each year, the boundary between forest and river disappears. Solid ground yields to rising water, and familiar pathways become submerged beneath a broad inland flood. Among the most remarkable expressions of this transformation is the Igapo, the seasonally flooded blackwater forest. Although it ranks among the least studied environments on Earth, it becomes one of the most productive stages in the Amazon, where towering trees, drifting currents, and immense predators briefly occupy the same living space. The annual flood reshapes the landscape with extraordinary speed. Rain falling across distant parts of the basin eventually reaches the river, lifting water levels until forests stand partially submerged. Dark water spreads through the trunks, carrying dissolved organic compounds released from decaying vegetation, giving the flooded forest its distinctive color. The Igapo usually remains inundated for approximately 4 to 6 months before the water gradually retreats, exposing the forest floor once again. During that interval, animals that normally occupy separate habitats begin sharing the same temporary world. Large predators respond almost immediately to this seasonal expansion. Anacondas move through the warm, shallow channels winding between submerged trees, where buoyancy allows their enormous bodies to travel with little effort. Mammals displaced by the flood gather upon isolated patches of higher ground or attempt to cross newly formed waterways, creating predictable opportunities for ambush. The flooded forest becomes an extension of the river itself, greatly increasing the hunting territory available to these immense reptiles without requiring long journeys into unfamiliar environments. Black caimans also patrol the changing boundary where permanent water meets newly flooded woodland. They drift among tree trunks and floating vegetation, waiting where animals enter or leave the water. The shifting shoreline concentrates movement into narrow corridors, allowing these predators to exploit natural bottlenecks created entirely by the seasonal rise of the river. Every flood redraws the landscape, yet similar patterns emerge with remarkable consistency as generations of predators respond to the same recurring cycle. Other giants take advantage of resources found nowhere else during this part of the year. Arapaimas swim into flooded forests to feed upon fruits dropping from overhanging branches, along with insects and other small animals attracted to this temporary habitat. Researchers have discovered individuals living miles from permanent river channels, surviving within shallow seasonal pools that exist only while floodwaters remain. When water levels begin falling, these remarkable fishes gradually return to deeper rivers, carrying the energy gathered during months of exceptional abundance. Navigation within the Igapo depends upon senses extending beyond ordinary vision. Sunlight struggles to penetrate dark water filled with suspended organic material, leaving many hunters to rely upon vibration, electrical signals, pressure changes, or other specialized sensory systems while searching among submerged roots and trunks. The forest becomes an intricate three-dimensional hunting ground where movement, rather than sight alone, reveals the presence of prey. This yearly flood pulse supports the entire community of giant predators described throughout this story. The temporary expansion of habitat increases feeding opportunities, strengthens breeding populations, and transfers enormous amounts of biological energy back into the permanent river system as waters recede. The flooded forest appears only for part of the year, yet its influence continues long after dry ground returns, sustaining the extraordinary scale of life that has evolved alongside the Amazon's enduring rhythm. Discovery often arrives with less certainty than people imagine. Even in the modern age, one of the largest animals on Earth can spend generations known locally while remaining only partially understood by science. The northern green anaconda illustrates this reality. Although recognized as a distinct species only recently through detailed genetic and anatomical study, the snake itself had shared its rivers with indigenous communities for countless generations. Scientific names can appear in an instant, while the living animal has already occupied its place in the forest for ages beyond written memory. That pattern extends across much of the Amazon basin. Every major expedition into remote regions has the potential to uncover animals never formally described, plants with no scientific name, or insects unlike any preserved in museum collections. Researchers continue to document mammals, birds, fish, amphibians, and reptiles that expand the known diversity of the world's largest rainforest. Each discovery suggests that many more remain beyond the reach of current surveys, living in valleys, flooded forests, and isolated tributaries visited only rarely by scientists. Even some celebrated giants remain difficult to measure. The arapaima is among the largest freshwater fish on Earth, yet no reliable estimate exists for its total population across the basin. Its movements through remote waterways, seasonal floodplains, and deep channels make comprehensive surveys extraordinarily difficult. Many rivers remain inaccessible for long periods, and individuals may travel between habitats that change dramatically as water levels rise and fall with the annual flood cycle. The piraíba catfish presents similar challenges. This immense predator can reach about 9 feet, which is about 2.7 meters, and occupies enormous stretches of river connected by thousands of waterways. Reports of exceptional individuals continue to appear, although the true maximum size remains uncertain because very large specimens are encountered infrequently and are not always documented using scientific methods. Population numbers also remain incomplete across much of its range, leaving important questions about distribution and abundance unanswered. Scientists estimate that tens of thousands of Amazon species have yet to receive formal scientific descriptions. Many are expected to be insects, fungi, and microscopic organisms, though larger fish, reptiles, amphibians, and mammals may still await careful documentation in isolated landscapes. The basin covers an immense network of habitats, each shaped by different soils, rivers, flood patterns, and forests. Exploring every corner is a task that stretches far beyond any single generation of researchers. Indigenous communities preserve detailed knowledge gathered through continuous observation across centuries. Their oral traditions describe animal behavior, seasonal movements, breeding cycles, and unfamiliar creatures that science has not always investigated. In many instances, ecological knowledge shared by indigenous peoples has later aligned with scientific discoveries, encouraging greater collaboration between traditional knowledge and modern research. Together, they reveal a richer picture of the forest than either perspective could achieve alone. For all its maps, satellites, and laboratories, science still sees only part of this living world. Each expedition fills a few more pages, while countless others remain unwritten. The Amazon continues to hold immense biological richness beyond complete human understanding, reminding us that the largest rainforest on Earth is still revealing its story, one careful discovery at a time. Long before scientific papers gave the northern green anaconda its own name, another form of knowledge had already marked its presence. Among the Waorani people of Ecuador, stories and practical experience described unusually large anacondas that differed from those known elsewhere across South America. These observations were not casual impressions gathered over a few seasons. They were carried through generations of hunting, travel, and daily life beside rivers where human memory stretched far beyond the span of modern scientific expeditions. When researchers eventually began examining these reports in greater detail, they discovered that local accounts aligned with biological evidence. Lead researcher Jesus Rivas had suspected for more than 15 years that another green anaconda species might exist. His suspicion grew through repeated observations, measurements, and descriptions that did not fit populations farther south. Reports shared by indigenous communities became another valuable piece of the puzzle, pointing toward differences that deserved careful, scientific investigation rather than dismissal. The expedition that formally described the northern green anaconda depended on more than technical equipment and laboratory analysis. It also depended upon trust. The Waorani people granted researchers permission to enter the Baihuari Waorani territory according to conditions established by the community itself. Local guides led the team through waterways and forest known through lifelong experience, making it possible to reach habitats that visiting scientists would have struggled to locate without assistance. Access alone was only part of the contribution. Knowledge accumulated across countless seasons helped researchers understand where unusually large snakes could be found, how they moved through the landscape, and which waterways were most likely to hold them. Without that partnership, the northern green anaconda may have remained scientifically undescribed for many more years, despite living in the same rivers throughout that entire time. This pattern extends far beyond a single species. Studies conducted across the Amazon have repeatedly shown that indigenous ecological knowledge can identify animal behavior, seasonal movements, habitat preferences, and population distributions that conventional wildlife surveys sometimes overlook. Scientific field methods provide measurements, genetic analysis, and standardized observations. Indigenous tracking traditions contribute generations of continuous experience gathered across landscapes visited year after year. Together, these approaches create a fuller understanding than either could achieve independently. Researchers studying Amazon wildlife have also recognized that conventional survey techniques often underestimate animal abundance in remote forests, where visibility is limited and access is difficult. Local experts who understand tracks, feeding signs, nesting areas, migration routes, and seasonal changes frequently locate species with greater consistency because they interpret subtle details that visiting teams may never notice during shorter expeditions. Such collaboration has become increasingly valuable as conservation efforts expand across the basin. The Amazon still holds discoveries waiting beyond the edge of present knowledge, although many of those discoveries are already familiar to the people who have shared this landscape for thousands of years. Rivers, forests, and flooded plains preserve remarkable biological diversity, while indigenous communities preserve equally remarkable knowledge of how life moves through them. Science continues to advance most effectively when observation, respect, and cooperation travel together, allowing the forest to reveal its stories through many voices instead of only one. For millions of years, the great reptiles and fishes of the Amazon have lived through changing rivers, shifting forests, and climates that unfolded across immense stretches of time. Their bodies adapted to gradual change, matching growth and reproduction to conditions that remained favorable over countless generations. Today, they face a different kind of transformation, measured not in millions of years, but within the span of a human lifetime. The same warmth that has long supported these animals also defines the limits of their survival. Cold-blooded creatures depend on surrounding temperatures to regulate every process within their bodies. As water becomes warmer, digestion speeds up, muscles respond more quickly, and growth can accelerate, provided temperatures remain within a suitable range. Once that range is exceeded, the pattern reverses. Metabolism demands more energy, stress hormones rise, reproduction declines, and prolonged exposure can increase mortality even when food remains available. Across parts of the Amazon basin, river temperatures have shown measurable warming during recent decades. The causes differ from place to place, although two influences appear repeatedly. Climate change has raised air temperatures across much of the region, while deforestation removes the forest canopy that once shaded countless streams and tributaries. With less cover protecting the water from direct sunlight, many smaller waterways absorb additional heat throughout the day, altering conditions for the animals that depend upon them. The forest itself changes alongside the rivers. Seasonal flooded forests, including the Igapo, rely upon predictable cycles of rainfall and overflowing channels. These habitats provide feeding grounds where fish, reptiles, birds, and mammals gather during months when rising water reaches deep among the trees. If forest loss continues or seasonal flooding becomes shorter or less extensive in some regions, the abundance of prey that supports large predators may also decline. Giant anacondas, black caimans, arapaimas, and other large hunters ultimately depend upon that seasonal surge of biological productivity. Climate models suggest that portions of the Amazon could experience longer dry seasons and more frequent drought under continued global warming, although future changes will not occur evenly across the entire basin. Reduced flood depth or shorter flood duration would shrink the temporary aquatic forests that serve as feeding grounds each year. Animals may be forced to travel farther between productive habitats, spending more energy while finding fewer opportunities to replenish it. There is another contrast between the present and the distant past. These lineages endured continental reshaping, dramatic shifts in global climate, and multiple mass extinction events through Earth's history. Those transformations generally unfolded across thousands to millions of years, allowing ecosystems opportunities to adjust. The environmental pressures now affecting the Amazon are developing far more rapidly, leaving less time for long-lived species with slow reproductive cycles to adapt through natural selection. The future of the Amazon's cold-blooded giants therefore depends upon more than their remarkable biology. Their survival remains connected to healthy rivers, intact forests, seasonal floods, and the delicate thermal balance that has sustained them across deep time. The conditions that once encouraged extraordinary size still exist across much of the basin, yet they have become increasingly dependent upon choices made far beyond the winding channels where these remarkable animals continue their enduring lives. An ecosystem can be understood through the lives of its smallest inhabitants, yet its overall balance is often maintained by only a handful of dominant predators. Across the Amazon, The black caiman, the green anaconda, and the arapaima occupy that role. They are more than impressive survivors living within an already functioning environment. Through their feeding habits and long presence in the river system, they regulate populations, influence animal behavior, and help preserve the relationships that allow countless other species to exist together. The black caiman stands at the highest level of the Amazon's aquatic food web. Its diet includes fish, turtles, birds, mammals, and smaller reptiles, with prey changing according to season, habitat, and opportunity. By removing vulnerable, abundant, or weakened individuals, black caimans help prevent certain prey populations from becoming excessively dominant. Their presence also changes how other animals move through the landscape. Fish avoid particular channels. Mammals approach riverbanks more cautiously, and aquatic communities remain dispersed instead of concentrating in a few favorable locations. Predation shapes behavior as much as numbers. During the 20th century, extensive commercial hunting for crocodilian skins caused black caiman populations to decline dramatically across many parts of the Amazon basin. Ecologists later documented ecological changes that accompanied those losses, although the exact effects differed from one region to another. Fish communities shifted, interactions among predators changed, and food webs became less stable in some waterways. These observations reflected a broader ecological principle recognized around the world. Removing an apex predator often produces consequences that extend through multiple levels of the ecosystem, even when the first changes appear subtle. The arapaima provides another layer of regulation within flooded forests and river channels. As one of the largest freshwater fishes on Earth, it feeds upon many smaller fish species, along with crustaceans and other aquatic prey. Because it breathes atmospheric air, it remains active in warm waters where dissolved oxygen is limited, allowing it to hunt successfully during seasonal floods. Its continued presence influences which fish populations flourish in temporary flooded habitats and which remain naturally limited through predation. Green anacondas contribute in a different but equally important way. They consume capybaras, caimans, birds, deer, fish, and many other animals depending on local conditions and individual size. Their flexible diet spreads hunting pressure across numerous species instead of focusing upon a single prey animal. This broad feeding strategy reduces the likelihood that any one large herbivore or aquatic predator will dominate available resources. Large snakes, therefore, become another balancing force within the network of interactions that supports the flooded forest. Ecologists describe these connected relationships as trophic cascades. Changes affecting predators near the top of the food web spread downward through herbivores, smaller carnivores, vegetation, nutrient cycling, and habitat structure. Some consequences appear rapidly, while others emerge only after many breeding seasons have passed. The Amazon's largest cold-blooded hunters therefore perform functions that reach well beyond their own survival. They strengthen the resilience of one of Earth's richest ecosystems. They are not decorative features placed upon an already complete landscape. They form part of its structural foundation, helping sustain the intricate balance that has developed across the basin through immense spans of time. Numbers can sometimes reveal less than absence. Across much of the Amazon, the largest animals leave traces in mud, ripples across dark water, and stories carried between communities, while exact population counts remain uncertain. Even after generations of research, scientists still know far more about the lives of these giants than about how many of them remain. The black caiman offers one of the clearer pictures. After decades of relentless hunting for its valuable skin during the 20th century, Many populations collapsed across the basin. Legal protection and conservation programs have allowed the species to recover in several regions, although estimates still place the total population at only a fraction of what once existed before commercial hunting reached its peak. Many researchers estimate that between roughly 25,000 and 50,000 mature black caimans remain across much of their range, though the exact figure continues to change as surveys improve and local populations recover at different rates. The green anaconda presents an even greater challenge. No reliable basin-wide population estimate exists, and scientists cannot confidently say how many individuals inhabit the rivers, swamps, marshes, and flooded forests of the Amazon. Their preference for remote waterways, dense vegetation, and water clouded with sediment makes conventional surveys extremely difficult. Even large adults can remain concealed for long periods, disappearing beneath floating plants or resting among submerged branches. Their numbers remain one of the largest unanswered questions surrounding Amazon wildlife. The arapaima tells a different story. In waterways close to towns and villages, decades of heavy fishing greatly reduced the number of giant adults. Individuals exceeding 6 feet, which is about 183 centimeters, have become much less common in many accessible rivers. The largest breeding fish, those that once dominated these waters for millions of years, were often removed first, reducing the number of exceptionally large individuals contributing to future generations. Even so, the species has demonstrated remarkable resilience. Community-managed fishing reserves across parts of Brazil have shown that arapaima populations can recover within only a few years when harvests are carefully regulated and breeding adults are protected. The piraíba catfish remains one of the least understood giants of the Amazon. No dependable population estimate exists for this immense predator. Its preference for deep channels, long migrations, and remote stretches of river places much of its life beyond regular observation. Researchers continue discovering new details about its movements, while basic questions about abundance across the basin remain unresolved. Even creatures that are not presently considered threatened depend upon habitats that continue to shrink. The Goliath birdeater tarantula still occupies wide areas of Amazon forest, yet its survival depends on undisturbed ground where burrows remain stable beneath the leaf litter. As forests disappear through clearing and fragmentation, suitable habitat becomes increasingly divided into smaller patches. Viewed together, these stories share a common thread. Animals that endured continental upheaval, shifting rivers, changing climates, and countless generations now face pressures developing within a human lifetime. Deforestation, warming waterways, habitat fragmentation, and selective removal of the largest individuals are reshaping populations far faster than many of these remarkable creatures can respond. Legends often grow faster than the creatures that inspire them. Across the Amazon, stories of enormous green anacondas have circulated since the first European expeditions reached South America during the 16th century. Travelers return describing snakes measuring 40 feet, 50 feet, or even 100 feet in length. Each generation repeated the tales, adding another layer to the mythology of the rainforest. Yet, despite centuries of exploration, no specimen approaching those extraordinary dimensions has ever been scientifically documented or verified through careful measurement. Modern field research tells a more reliable story. For more than 3 decades, lead researcher Jesus Rivas studied green anacondas throughout their natural range, examining well over 1,000 individual snakes. Among the largest he personally documented was an exceptional female from Venezuela, measuring 5.21 meters, which is about 17 feet and weighing 97.5 kilograms, which is about 215 pounds. It remains one of the largest wild anacondas ever carefully measured and described in scientific literature. Adult females consistently grow much larger than males, making them the giants responsible for nearly every authenticated size record. Scientists do not rule out the possibility that even larger individuals exist in remote parts of the Amazon. A snake living for many years in an undisturbed habitat could exceed the dimensions of currently documented specimens. Even so, there is no verified evidence supporting the enormous lengths commonly repeated in popular stories. Estimates suggesting maximum lengths approaching 27 or 29 feet remain speculative rather than scientifically confirmed. The largest verified animals are still extraordinary without extending beyond the available evidence. The enduring fascination with giant anacondas has inspired repeated attempts to prove the legends true. National Geographic has long maintained a standing reward for credible documentation of an anaconda exceeding 30 feet, which is about 9.1 meters. Decades have passed without anyone successfully claiming that reward. Numerous photographs, stories, and eyewitness accounts have appeared, yet none has satisfied the standards required for scientific verification. One famous example emerged during 2016 when photographs spread rapidly across the world, claiming construction workers in Brazil had uncovered a 33-foot anaconda weighing 880 pounds. News organizations, websites, and social media repeated the story almost immediately. Later investigation showed the photographs had been taken in different circumstances and paired with unsupported measurements. The spectacular claims collapsed under closer examination, leaving another reminder that remarkable images do not always represent remarkable evidence. The genuine animal hardly needs embellishment. A green anaconda measuring around 20 feet in length and weighing several hundred pounds ranks among the heaviest snakes ever known. Its muscular body moves through water with remarkable efficiency, disappearing beneath the surface until little remains visible beyond its eyes and nostrils. Encountering such an animal in the flooded forests would challenge anyone's sense of scale. Perhaps that explains why the stories endure. The Amazon remains so immense, so difficult to explore completely, that imagination naturally expands into places where observation is limited. The legends reveal something meaningful about the rainforest itself, while the verified anaconda reminds us that reality, measured with patience and evidence, is already astonishing. Time leaves different signatures on different creatures. Some lineages reinvent themselves again and again, while others arrive at an effective design and carry it across millions of years with only subtle refinements. Many of the Amazon's largest cold-blooded animals belong to that second story. Their ancestors watched landscapes transform, rivers change direction, and mountains rise, while the foundations of their bodies remained strikingly familiar. Among the oldest of these living giants is the arapaima. Fossil evidence indicates that this remarkable fish has occupied the Amazon region for at least 13 million years, stretching back into the Miocene epoch. Across that immense span, its elongated body, air-breathing ability, and powerful scales have required surprisingly little alteration. Natural selection continued shaping details of its biology, yet the overall design remained remarkably successful. Long before people traveled these waterways, the arapaima had already become one of their dominant inhabitants. The ancestry of the green anaconda reaches just as deeply into the continent's history. Fossil discoveries and evolutionary studies show that giant anacondas were already present in northern South America roughly 12 million years ago. Although scientists continue refining estimates of their maximum ancient size, the evidence demonstrates that these snakes had already evolved into formidable predators while the Amazon drainage system itself was still developing. Their success did not depend upon sudden evolutionary innovation. It rested on a body plan well suited for warm wetlands, rich with aquatic prey. Crocodilians carry an even longer history. The broader group that includes the black caiman has existed for roughly 80 million years. Relatives of today's crocodilians survived the asteroid impact that ended the reign of the non-avian dinosaurs, then continued through profound climatic shifts that reshaped forests, coastlines, and river systems around the globe. Modern caimans differ from those distant ancestors in meaningful ways, yet the essential arrangement of armored body, muscular tail, powerful jaws, and patient hunting strategy has endured across extraordinary stretches of geological time. The electric eel represents another enduring solution. Members of its lineage have generated powerful electrical discharges for millions of years using specialized organs formed from modified muscle tissue. Human inventors drew inspiration from these natural electrical systems centuries ago while exploring the principles that eventually led to the development of the earliest batteries. The eel itself required no redesign to demonstrate those capabilities. Evolution had refined the mechanism long before human civilization began investigating electricity. None of these animals appeared after the Amazon reached its modern form. Their histories unfolded alongside the landscape itself. Beginning around 25 million years ago, the continuing uplift of the Andes Mountains altered the flow of rivers across northern South America. Water that had once drained westward became trapped within immense lowland basins before gradually carving an eastward route toward the Atlantic Ocean. Wetlands expanded, floodplains spread across broad valleys, and new ecological opportunities emerged through countless generations. As those environments changed, the great predators changed with them. The Amazon did not arise for their benefit, nor did they arrive fully formed within a finished rainforest. Their evolutionary paths became intertwined across millions of years, each influencing the other through the steady rhythm of geological change, adaptation, and survival. The giants living there today remain living chapters from that shared history, carrying bodies shaped by a world that has never truly stopped becoming. A map can give the comforting impression that a place has been fully understood. Blue rivers trace across green landscapes, borders appear with crisp certainty, and names settle onto the page as though they complete the story. The Amazon resists that illusion. Its outlines have been drawn for centuries, yet much of its living world remains only partly explored, especially within remote forests, floodplains, and waterways where biological surveys have reached only scattered locations. The Amazon basin covers approximately 2.7 million square miles. That is nearly 7 million square kilometers, which is about 4,350,000 square miles. Satellites now reveal the shape of its forests with extraordinary precision, recording the spread of rivers, the rise of mountains, and the scars left by deforestation. Even so, images captured from orbit cannot reveal every animal moving beneath dark water, inside hollow trees, or within dense vegetation. A landscape may be mapped while much of its biological richness remains undocumented. The scale of what remains to be discovered became clear during a Conservation International scientific expedition conducted during 2026. Working in a remote region for only a few weeks, researchers documented 536 bird species, 151 mammal species, 68 fish species, and hundreds of additional organisms. Among the mammals were species previously unknown to science, while several fish had never before been formally described. One carefully studied region expanded scientific knowledge in ways that decades of broader assumptions never anticipated. The northern green anaconda offers another reminder that remarkable discoveries can still emerge from familiar looking landscapes. Formally recognized as a distinct species during 2024, it ranks among the largest animals on Earth. Its existence had never been entirely invisible. Indigenous communities had long recognized differences between these snakes and populations farther south. Scientific confirmation arrived only after researchers combined genetic evidence, detailed measurements, and generations of local ecological knowledge gathered from people who knew the region intimately. Biologists estimate that the Amazon contains roughly 1/10 to 1/6 of all known living species on Earth, while countless additional organisms remain unnamed. Small insects, fungi, freshwater invertebrates, plants, and microorganisms account for much of that hidden diversity. Every expedition into previously undersampled habitats continues adding new entries to scientific catalogs, demonstrating that the inventory of Amazonian life remains unfinished despite centuries of exploration. Freshwater fishes illustrate this uncertainty especially well. Thousands of species have already been described across the basin, making the Amazon the richest freshwater fish ecosystem known. Specialists expect many additional species to be identified, particularly among catfishes and other groups occupying isolated tributaries and deep channels. Some may grow to impressive sizes, although such discoveries cannot be predicted with certainty until specimens are carefully documented and studied. The greatest mystery is therefore not a legendary creature waiting beyond the next bend in the river. It is the immense abundance of ordinary life that has never received a scientific name. While forests are cleared and waterways continue changing, opportunities to understand those species diminish. The Amazon remains one of Earth's least completely documented biological worlds, and its unwritten chapters are disappearing even as researchers continue turning the pages. Across millions of years, evolution has explored many different ways to remain alive. Some creatures carried their own furnace wherever they traveled, spending immense amounts of energy to keep their bodies warm through changing seasons and shifting climates. Others followed a different path. They accepted the rhythm of the world around them, drawing warmth from sunlight, water, and air instead of producing it themselves. Deep within the Amazon, that second strategy reached extraordinary expression. The largest snake on Earth glides through floodwaters without maintaining a constant internal temperature. One of the greatest freshwater predators relies on the same principle. The arapaima, whose lineage stretches back at least 13 million years, still follows it today. Even the electric eel, whose remarkable biological abilities helped shape humanity's early understanding of electricity, depends upon the surrounding environment for warmth. These animals differ greatly in appearance and behavior, yet they are connected by the same fundamental biological pattern. Warm-blooded animals are often presented as the pinnacle of evolutionary success. Constant body temperature allows activity through cold nights, harsh winters, and environments that would limit many other creatures. That flexibility opened opportunities across mountains, deserts, polar regions, and nearly every landscape on Earth. Such independence, however, carries a tremendous energetic cost. Every hour demands fuel to keep the body's internal furnace operating, whether food is plentiful or scarce. Within the Amazon, those costs shift the balance. Heat surrounds every river, flooded forest, and marsh for much of the year. Cold-blooded animals can devote less energy to generating warmth and more toward growth, survival, and reproduction. Across countless generations, that energy economy helped produce snakes weighing more than 550 pounds, fish capable of reaching extraordinary size, and crocodilians whose ancestors have endured since the age of dinosaurs. Their achievements emerged through efficiency, shaped by a remarkably stable environment. Biology does not assign meaning to these outcomes. Natural selection carries no preference for elegance, courage, or ambition. It favors whatever traits allow organisms to leave descendants under the conditions they encounter. In the Amazon, abundant warmth and seasonal floods rewarded creatures able to synchronize their lives with the changing landscape instead of resisting it. Those conditions produced giants whose existence can seem almost improbable when viewed through human expectations. Each of these animals continues following principles established near the beginning of life itself. Energy is gathered when opportunities appear. Growth continues while resources allow. Reproduction secures another generation. Success depends upon fitting into the surrounding world instead of standing apart from it. Over immense spans of time, that uncomplicated pattern proved powerful enough to survive continental transformation, climatic upheaval, and the rise and disappearance of countless competing species. Perhaps that is what lingers after every remarkable measurement, every fossil, and every expedition fades into memory. The Amazon offers warmth, water, shelter, and astonishing abundance. Its great cold-blooded inhabitants answer with patience measured across geological ages. Together they reveal that evolution possesses no single destination, only many different paths shaped by place and time. Among those paths, one produced the remarkable giants, whose lives have drifted through this story from beginning to end. Fear often begins long before thought. A sudden shape in dark water, the outline of broad jaws resting at the surface, or the suggestion of an immense body passing beneath floating leaves can awaken responses carried from a distant evolutionary past. Those reactions belong to us. The creatures themselves are occupied with lives that have unfolded in much the same way for millions of years, entirely independent of human imagination. The anaconda never became enormous to inspire stories or motion pictures. Its immense body allows it to overpower prey that smaller snakes could never restrain, while storing energy that can sustain long periods between meals. The electric eel did not evolve the ability to release discharges approaching 860 volts to alarm people traveling rivers. That remarkable ability serves practical purposes, locating prey, defending against predators, and navigating through dark, sediment-filled water where vision offers little help. Every extraordinary feature seen in these animals emerged through natural selection, acting on survival, never on spectacle. The Amazon has always demanded exceptional solutions. Large prey reward large hunters. Dense forests and winding waterways create countless places to hide, yet they also conceal countless dangers. Competition unfolds across every level of the food web. Success belongs to organisms whose bodies solve the challenges placed before them with slightly greater efficiency than those around them. Across immense spans of time, those small advantages accumulated until they produced animals that appear almost impossible when viewed through modern human eyes. Our response to them follows a different history. For millions of years, the ancestors of human beings lived alongside formidable predators. Large reptiles, powerful snakes, and concealed ambush hunters represented genuine dangers within many prehistoric environments. Natural selection favored individuals who detected potential threats quickly and reacted before certainty arrived. The instinct remains deeply rooted, even when knowledge replaces immediate danger. A glimpse of a massive snake still reaches ancient parts of the human mind before careful reasoning has an opportunity to speak. That inheritance deserves understanding without requiring exaggeration. Respect for these animals grows from recognizing what they truly are instead of transforming them into monsters. An anaconda resting within a flooded forest is not contemplating human observers. It does not construct legends about distant primates. Its body processes the warmth gathered from the surrounding environment. Digestion continues. Muscles remain prepared for the next opportunity presented by the river. Generation after generation has repeated that same pattern across approximately 12 million years, requiring neither drama nor intention. Modern humanity has existed for roughly 300,000 years, only a brief interval compared with the history carried inside these lineages. During that time, rivers shifted, forests expanded and contracted, climates changed, and civilizations appeared. The great cold-blooded inhabitants of the Amazon continued following biological rhythms established long before the first human settlement emerged. Their persistence does not diminish our own story. It places it within a broader chronology, where many successful forms of life have endured through patience instead of haste. Perhaps the deepest unease these animals awaken comes from recognizing that they owe us nothing. They neither welcome nor reject our presence. They exist according to rules written by evolution across geological ages, reminding us that the oldest powers within the Amazon were never created for human attention. They were already there, and our encounter with them reveals as much about ourselves as it ever reveals about them. There comes a point when every landscape asks something of those who have learned its story. The Amazon asks for nothing spoken aloud. It offers no judgment and makes no promises. Its rivers continue their winding paths. Its forests continue exchanging water with the sky, and its oldest inhabitants continue following rhythms established across millions of years. Yet another rhythm now moves through the basin, one measured by chainsaws, roads, fires, and the gradual disappearance of places that once seemed beyond human reach. In recent years, the Amazon has lost roughly 10,000 square miles of forest during some 12-month periods, an area close to the size of the state of Massachusetts. Every stretch of forest removed changes more than the view from above. The leafy canopy that once shaded rivers gives way to direct sunlight. Water absorbs more heat. Seasonal flooded forests, known as agapo, become less stable, where altered rainfall and damaged landscapes reduce the floods that sustain them. As those seasonal waters shrink, fish, mammals, reptiles, and birds lose the abundance that once gathered them together. Predators that depended upon those gatherings must search farther while finding less. The great animals encountered throughout this journey have endured extraordinary chapters of Earth history. Their ancestors lived through the changing rivers of the Miocene, crossed into the cooler climates of the Pliocene, persisted across the advancing and retreating ice ages of the Pleistocene, and belonged to lineages that survived multiple mass extinctions across geological time. Their history reveals endurance on a remarkable scale. Resilience, however, has always depended upon the continued existence of the living system surrounding them. Even the strongest predator cannot remain where the web of life supporting it gradually comes apart. Geological change usually unfolds across spans so immense that evolution has opportunities to respond. Rivers alter course over countless generations. Mountains rise with almost imperceptible patience. Forests shift gradually as climates transform. The pressures shaping the Amazon today move according to another clock. Roads appear within years. Forests disappear within seasons. Rivers respond within decades. The difference lies less in the existence of change than in its pace, leaving far less time for living communities to adjust before familiar conditions have already vanished. No simple conclusion waits at the end of that realization. Biology offers observations instead of moral verdicts. Each tree removed carries away habitats assembled through countless generations. Each disappearing population represents more than a collection of individual animals. It contains evolutionary solutions refined across approximately 12 million years for giant anacondas, at least 13 million years for arapaima, and far longer for the crocodilian lineage itself. Those solutions cannot be recreated within a human lifetime once they disappear. The Amazon does not ask for admiration alone. Its history invites perspective. Every giant explored throughout this story stands as living evidence that nature can build extraordinary forms when given enough time and enough continuity. What is ultimately at stake reaches beyond individual species. It is the preservation of a biological inheritance written across millions upon millions of years, one that still endures within the rivers and forests today, provided the living system that shaped it is allowed to endure as well. Night settles across the Amazon without ceremony. Warm rivers continue their endless movement through flooded forests, carrying drifting leaves, suspended sediments, and reflections that dissolve with every ripple. Somewhere along those winding channels, a broad head rises for a single breath before slipping beneath the surface again. Nearby, another shape remains almost motionless among the reeds. Farther away, an immense body glides through dark water with no need for haste. The oldest rhythms of this place continue exactly as they have through ages almost beyond imagination. An arapaima breaks the surface, drawing air into lungs that have served its lineage for at least 13 million years. A black caiman waits along the water's edge, watching with remarkable patience until opportunity passes close enough to matter. An anaconda settles within the shelter of submerged vegetation, conserving energy gathered from the warmth surrounding it. None of these lives unfolds with urgency. Each follows patterns refined across spans of time, far greater than the history of our own species. They possess no awareness that people have crossed continents searching for them. They do not know that their scales and armor have inspired engineers studying protective designs, or that the astonishing electrical abilities of the electric eel helped shape humanity's earliest understanding of bioelectricity and encouraged discoveries that contributed to the development of modern electrical science. They know nothing of research expeditions, scientific papers, museum collections, satellite images, documentary films, or stories shared across the world. Those belong entirely to us. Their existence remains centered upon simpler necessities. Warm water sustains bodies that rely upon the surrounding environment for heat. Seasons determine when forests flood and when prey gathers. Hunger arrives, is answered, and fades again. Reproduction continues whenever conditions allow. Young animals begin the same journey, followed by countless generations before them. Life proceeds without ambition, reputation, or recognition. Across immense stretches of geological time, that uncomplicated persistence has proven remarkably successful. Perhaps that enduring simplicity explains why these creatures seem almost timeless. They have never needed to dominate every landscape or occupy every climate. They flourished by fitting precisely into one extraordinary place, responding to its rivers, forests, temperatures, and seasons with patient consistency. The Amazon, in return, became one of the richest living systems ever to exist, shaped through continuous exchange between geology, water, climate, plants, and the remarkable animals that found lasting homes within it. Even now, many reaches of the basin remain scarcely explored by modern science. Countless waterways have yet to receive careful biological surveys. Beneath floating vegetation, inside winding tributaries, and within forests that flood each rainy season, life continues according to rules established long before the first human footsteps entered South America. Somewhere within that living network, another great body moves through the current, gaining strength one meal at a time, guided by biological instructions carried across millions of years. The river asks nothing of an observer except attention. It continues flowing, whether anyone watches or not. Within that current, giants endure without seeking admiration, carrying forward histories older than mountains, older than familiar coastlines, and older than humanity itself. Their world remains alive tonight, still unfolding beyond the edge of what we know, following the same enduring pattern that has sustained it since deep time first shaped the Amazon into the remarkable place it remains today.